Go ahead and talk now. Start now.
Yes, sir.
Okay. Welcome. This is the second lecture for the Multimodality Imaging Conference. Last lecture we talked about the general applications for physics of sound and ultrasound specifically, and the Doppler equation was introduced. Today we will talk about how to use Doppler to quantify flow and estimate pressure gradients, and sometimes we can estimate pressures. We'll go through very basic steps at first, so we are all on the same page about what we are measuring and why the expressions that you see down later on in the presentations appear. So pressure is defined as force per cross-sectional area. Remember, for the cardiovascular system, we are interested in fluids. And so there will be, as you see later on, derivations to convert or to use data that apply to fluids. So if you apply the SI system, force can be the pressure can be expressed as dynes per centimeter squared or Newton per meter squared. 1 Newton per meter squared is 1 Pascal. So for the Newton, the mass is in kilograms and the acceleration is in meter per second squared. Let us look at what are the possible derivations for pressure from that expression. So from Newton's second law, we can remove force and put in its place mass multiplied by acceleration. And still we are in the pressure expression that is divided by area. We do not measure mass necessarily for fluids, but we deal more with volume, and therefore we can remove the mass expression and put in its place density multiplied by volume. So now if we look at that first expression and we say volume is given by area multiplied by a third dimension, and then we sort of cancel that area, we end up with the expression of pressure being given by the product of density, acceleration, and distance. If we are looking at a stationary fluid at a certain height above the center of gravity, that acceleration becomes the free fall acceleration. And so frequently, and not frequently, usually what you will see expressed when we estimate pressures is in millimeters mercury or centimeters of water. So we need to see how we get to centimeters of water or millimeters of mercury from that expression. Density of water is 1, and so for a 1 centimeter of water, how much pressure does it exert? We put the density multiplied by the free fall acceleration. In meters per second, it's 9.8 meter per second squared. So in centimeters per second squared, it becomes 980. And for 1 centimeter of water, that's the pressure that it exerts in SI units. For 1 millimeter of mercury, we go back to that expression, but now mercury has a higher density than water, 13.6. We still put the 980, but because it is higher density, we do not necessarily use the centimeters, but we will use the millimeters. So here, instead of putting 1 centimeter, we will say 1 millimeter or 0.1 centimeter. And if you do the math, you will see 1333 dynes per centimeter squared. A frequent question that arises is, how can I convert from centimeters of water to millimeters of mercury? So you ask the question, 1 centimeter of water exerts pressure equal to 980. And so that 980 corresponds to how many millimeters of mercury if 1 millimeter exerts a pressure of 1333. So we divide the 980 by the 1333 and you end up with that number. So take home message. If somebody gives you the pressure in centimeters of water, you multiply it roughly by 0.74 and you end up with millimeters of mercury. Now let us talk about flow. We're looking at flow through a cylinder with a circular cross-section. And so if someone says, I want to know the flow going through that cylinder, the answer would be, if I know the volume of blood or of fluid in that cylinder, that can help me estimate the flow. So we go for volume and we say it's cross-sectional area, but instead of multiplying it by the length of that cylinder, we will multiply it by velocity, because this is flow that is taking place. And so you will see the units of flow centimeter cube per second. Of course, you can convert that to liters. We use two basic assumptions for the cross-sectional area, either a circle, and then we use the circle expression, or an ellipse. In some situations, it is more appropriate or it is more accurate to use an ellipse. For example, mitral annular area mimics more of an ellipse as opposed to a circle. Some veins, when you take a cross-section of them, it is more of an ellipse or ellipsoid even, as opposed to a circular cross-section. So if we use an ellipse, then we need to get the radius for the major diameter and for the minor diameter, and then we apply that expression. We'll come back to that equation several times through this presentation. So now let us look at the factors that govern flow in a tube. So as a fluid goes through a tube, and we are assuming a tube that is not elastic, it's not a tube that will expand. Of course, that's an approximation, and we'll see how that impacts our calculations down the line. But basically, the fluid, as it goes into that tube, is going to move with a fast or the highest velocity in the center. And then as you go from the center to the wall of that tube, the velocity will be decreasing, such that it ends up with that parabolic front. The distance from where the fluid enters to where that front is fully developed is referred to as the entrance length. The message I want you to remember from this slide is that fluid is stationary at the edge of that tube and has the highest velocity in the center. Similar to solid objects, where we talk about friction, here there is also some resistance to flow, and it is expressed using viscosity. A fluid that has a higher viscosity is offering higher frictional forces. Frequently, blood is described as a Newtonian fluid. What does that mean? It means that there is a linear relation between shear tension and velocity gradient. What is shear tension? If you have a cylinder and you are doing a cross-section of it, there are two types of tension in general that we can talk about. First, there is the normal tension that is applied perpendicular. Then there is tension that is coplanar with that cross-section. That's the shear tension we are talking about. And here we can express the relation between the shear tension and the velocity gradient. The velocity gradient here is a gradient of velocity over a distance, not over time. They are directly related, and the constant is viscosity. We are interested in knowing what are the units of viscosity, so we rearrange that expression, and now you will see the shear tension, which has the same units as the pressure, so we will put that Pascal. And if you look at that, it's distance divided by velocity, so you end up with the product of Pascal and second. These are the units of viscosity. We want to remember that as we go through other slides later on. Now let us talk about the factors or the forces that govern flow in a rigid tube. They also apply to a tube that is not rigid, but here we will have to do some assumptions and some approximations to convert from what you see in a rigid tube to an elastic tube. Let's start first with the rigid tube. Flow takes place from point 1 to point 2 because pressure at point 1 is higher than pressure at point 2. And there is a distance of L that we will refer to. That's the length of this tube. This could be a capillary, could be an artery, could be a vein, whatever the situation is. And then let's take a look at the cross-section. We will assume that the cross-section is a circle. As we mentioned earlier, if it is not a circle, then there are different set of expressions that we use. But we will say it's a circle, and we have concentric layers of fluid. As you go from the center to the outside, the radius gets larger and larger, such that the largest radius is A, and we'll say the radius at any cross-section can be expressed by the term R. Velocity is maximum at the origin, so we will refer to that as U origin. Velocity is 0 at the wall of that vessel, and in between the velocity will be less than the maximum velocity in the center, but more than zero. When we're looking at a state of equilibrium, then the forces that want fluid to move, this is the pressure gradient between the 2 points, are balanced by the frictional forces that want to stop the movement. Now let us see how we can express the pressure and the friction forces. So we are talking forces, meaning if I want to convert from pressure to force, then I multiply the pressure by the cross-sectional area, because pressure is force divided by cross-sectional area. Since it's a circle, you see that pi r squared. How about the frictional forces? Here we will say it's the shear tension multiplied by the area over which it's applied. And here it is the surface area of a cylinder. The surface area of a cylinder is given by the product of its circumference and length. And so let us rearrange that expression, and when we rearrange it, we remove the pi, as you see. We remove one of the r squared, and that's the first expression we are left with. But also you know that we just said that blood is a Newtonian fluid, and so that shear tension can also be expressed as the product of viscosity and the spatial gradient of the velocity. Let us again do some rearrangement. It's simply multiplying that dr by the expression on the left-hand side, and that's the first equation we have. Then we say let us integrate that expression over certain boundaries. And these boundaries are basically from the center to the edge. And so if you do that, we're going from the maximum velocity that can be encountered to a velocity of 0, and for the radius, from a radius of r at any level, at any cross-section of that concentric layer of fluid, to the maximum radius, which is a. If you integrate r dr, that is simply r squared over 2, and that's what we are left with. Notice that the minus signs cancel, and at the center the radius is really 0, and so that expression of the maximum velocity is given by the difference in pressure gradient multiplied by the radius squared divided by 4 multiplied by the length and the viscosity. We are interested not in the maximum velocity, but in a mean velocity, something that expresses the fluid throughout that cross-section, through the whole cross-section of that cylinder. So we will say the flow is area multiplied by velocity, as we saw in the second slide, and it can be shown that the mean velocity is roughly half the maximum velocity. We do the substitutions, and you see that the flow is given by the pressure gradient multiplied by the 4th power of the radius, inversely related to viscosity and the length. If you want to apply the concept of resistance similar to, say, electric circuits, you can say it's the voltage divided by the amperes. For us here it is the pressure gradient divided by the flow. And resistance is directly related to the length of that vessel, directly related to the viscosity, and inversely related to the 4th power of the radius. So of all the variables that you see here, the one that can carry a big influence is that radius, because it's to the 4th power. Okay, now that we've talked about the Poiseuille's law, let's say what are the problems or the challenges of applying that law to the flow in the circulation. The first one is the assumption that the viscosity is constant no matter where you sample the flow. This is not the case. Viscosity depends on the composition of the blood, and in some vessels the red blood cells may not easily get all the way in. And so this happens in vessels that are less than 0.5 to 1 millimeters. These are not examined by Doppler. So that issue of constant viscosity not applicable is not usually a major limitation. The second point is laminar flow. If we talk about the normal circulation, flow is mostly laminar except for very short distances in the pulmonary artery and the ascending aorta, the aortic root. Once you pass these very concrete areas, if you would, flow is indeed laminar. And so again, that's not a major limitation for normal flows. We are not talking about situations where there is vessel stenosis or valve stenosis. The third assumption is the circular tubes. And here, as you saw, all the derivation is based on that circular cross-section. And it doesn't apply for tapering vessels. The major problem for the extension of Poiseuille's law from rigid tubes to the circulation is the issue of inelastic tubes. The blood vessels expand during systole, and so that carries an error of at least 10%. Finally, flow in the circulation is pulsatile. It is not steady flow. Notwithstanding that limitation, if you're looking at an average over a period of time that is a temporal mean, it is not unreasonable to still think of the flow in terms of the Poiseuille's law that we just went over. Now let's talk about something called Reynolds number. Reynolds number is a number that determines whether turbulent flow will take place or not. And basically, it's the ratio of inertial forces to viscous forces. The higher the inertial forces compared to the viscous forces, the more likely that turbulent flow will happen. Viscous force is easy to express in terms of viscosity, and we just said that the units of viscosity are Pascal second. Let's now focus on the inertial forces, which may not be as easy to think of conceptually. The inertial forces of a fluid depend on its density. A fluid that is more dense has more inertia. Similar to a mass, if a given individual has a higher mass, that has a higher inertia. Also depends on velocity, directly related, and the diameter. In a sense, the diameter is a surrogate of the volume that will be moving. And so let us see how we get the numerator and whether it will be the same units as the viscosity, so we can prove that Reynolds number is indeed dimensionless. So for density, you can remove it. We're going to work only with that numerator. So we remove density and put in its place mass over volume, multiplied by velocity, multiplied by diameter. You can also remove mass and put in its place force divided by acceleration from Newton's second law. Now when you look at that numerator, it becomes force times velocity times diameter divided by acceleration and volume. Velocity is meter per second or centimeter per second, and acceleration is centimeter per second squared. So you end up with a force multiplied by second. And then diameter over volume, if you cancel the diameter with one of the dimensions from the volume, you are left with force over area. So that's the Pascal second, the same units as the denominator, and that's why that number is dimensionless. We already covered the flow. The simple take-home message is I want to get the cross-sectional area. I'll assume if it is a circle or an ellipse, and then I'll multiply that by the velocity. So I need to measure the diameter at the very least and to measure the velocity. We do a lot of calculations and derive the area. For example, the area of the left ventricular outflow tract. What are the sources of error when we do calculations? The first one is a diameter measurement. If the diameter, say, is 2.1 and I measure it 2.3 or 1.8, I made an error in the diameter. That, of course, will translate to an error in the flow. The second error is the geometric assumption. If I say it's a cross-section of a circle, but it is not a circle, then I will apply the wrong expression to get the area. The third problem is the issue of phasic flow and instantaneous area. Let us think of the aortic valve for a moment. If you were to look at the aortic valve area over the duration of systole, it is not constant. Not that there are large variations, there are small variations, but it will gradually increase as the flow goes up. So if I am interested, say, in the area at 1/3 the duration of systole after the QRS, then that could be different from the valve area at the end of ejection, say. Another error is absolute flow and changes in area. And again, that easiest perhaps to recognize, say, in the aortic valve area calculation. You are all familiar with the low ejection fraction patients with low flow, low gradient. And here we increase the flow and see what happens to the valve area. The idea, if there is a valve area that is small because of the flow being reduced. As you increase the flow, that valve area will increase, as opposed to a valve that is really small and no matter what you push through it, the area doesn't change. Another question is the appropriate site for measurement of diameter. The example I showed you where I'm measuring cross-section and velocity, I am measuring both at the same site. But say, can I use then cross-section, say at the level of the mitral valve and flow someplace in the ventricle and combine them to say this is the actual flow? No. Where you measure the velocity has to be the same place where you measure the area. Finally, to circumvent that issue of diameter and converting diameter to areas and the errors that can come from that, there were early on attempts to go after actual area measurements. While these are sort of more sound than trying to convert diameter to areas, turns out that the actual measurement of the area, say by planimetry, can also come with its own errors. So you can see a lot of potential for errors that can come when you try to obtain flow. A question that is frequently asked is how much a diameter error translates to an error in the area. Like if the diameter is 2.1 and I measure it 2 or 1.9. How much that translates to an area. Most people think of the expression of pi r squared and they think it's squared. It is not. That's a simple algebra approach to show you what it boils down to. But to cut a long story short, the error in the length really is multiplied by 2. And it's a twofold magnitude in the error that you will calculate in the area. That's why if we want to minimize the errors, we always want to use a scale that is more expensive as opposed to a scale that is crowded together. So we focused in the previous 2 slides on errors in diameter and area measurements. There can also be errors in velocity measurements. So the first one is the assumption that it's a uniform spatial velocity. No matter where you do the cross-section in that cylinder, the velocity is the same. We know that this is not the case, particularly if you're looking at areas of stenosis or ectasia being present in a vessel. When we get the spectral profile by pulse wave Doppler, sometimes we see different peaks, and the question becomes which one of these I choose. If I choose, say, the highest velocity as opposed to the most dense signal, I will end up with different velocity values. It would be best if we can quantify the 3D spatial velocity vector as opposed to 2D. That is possible, but can also be challenging, and there haven't been data showing that this results in a major improvement in the accuracy. Signal strength. Sometimes we have patients in the ICU on mechanical ventilation, and when you try to get the signal, because of the interference with air, you do not end up with a complete envelope. If I do not see a complete envelope, then I can make an error in tracing that velocity or that time velocity integral. We talked about non-simultaneous measurement of area and velocity. For example, flow through the LVOT. We get the diameter from the parasternal long axis, and then I have to go to scan from an apical view to get the velocity. If the heart rate is identical, the RR interval is identical, nothing has changed, that works. But say it's somebody with frequent ectopy or with atrial fibrillation, there can be differences. And lastly, the assumption of continuity. Let me give you an example. I want to quantify the stroke volume, and instead of me measuring flow in the LV outflow tract, I will measure it in the aortic root above the level of the coronary arteries. Would they be the same value? No, because some flow happened already to the coronary circulation. So we have to think of where we are measuring the flow and what that flow actually represents. How do we calculate cardiac output? That's a basic measurement that we include frequently in our reports, and usually we rely on Doppler. Of course, we can use 2D to calculate cardiac output as well. Stroke volume is given by the product of the cross-sectional area. So we say that is a circle or an ellipse. as we've seen how we get that area before, multiplied by the time velocity integral. Here you will see that the units, when you multiply them, have the units of volume, not velocity, because we're not quantifying flow, we are quantifying volume. Time velocity integrals can be obtained directly from the ultrasound system. The system can do them themselves, or someone can do that, or you can do them offline where you are reading and doing your measurements. In the older days, people were interested in some assumptions to cut corners. No reason to do that. You can say it looks like a triangle, and then you get it as the way you get the area of the triangle. And of course, if I have the stroke volume and I know the heart rate, then I have the cardiac output. This has been validated against invasive data with right heart catheterization, and when you have good quality Doppler data and when you do the studies simultaneous, there are excellent correlations. The application of Doppler echocardiography to quantify flow has been applied to look at drug therapy. For example, someone in heart failure who is placed on inotropic drugs to improve their cardiac output. Using different pacing modes, adjusting interventricular delay or atrioventricular delay to get the maximum cardiac output. Looking at physiologic changes that happen with pregnancy, delivery, and in the postpartum period. Looking at fetuses and neonates and their blood flow and their cardiac output. And also with exercise Doppler echocardiography. So let's look at some clinical applications of flow calculations, and we'll go through examples. One of these is shunts, left to right shunts. Regurgitant volume calculations, be it aortic, mitral, or pulmonic. Calculating the valve area, and even ejection fraction. For example, if I know the stroke volume by Doppler, and I'm satisfied with these Doppler signals, and I have an end diastolic volume by 2D, then I can compute the ejection fraction. How do we measure LVOT flow? So we go to the parasternal lung axis view, we zoom on the LV outflow tract, and then we measure that online. Notice that we've sort of zoomed in to avoid those errors in measurements that we talked about earlier when you use a crowded scale. Then we put the pulse wave Doppler sample volume in the LV outflow tract just below the aortic valve. You may see one of the clicks, but you should not see both opening and closing clicks. If you see both clicks, then you are in the valve, not in the outflow tract. And as you see here, you see flow only through the outflow tract. You do not see mitral inflow. If you're seeing mitral inflow with that, then you are not in the LV outflow tract, meaning we are angulated, meaning we can underestimate, and instead of a certain stroke volume, we cut that absolute value. For the right ventricular outflow tract, this tends to be more challenging. We can rely on a long axis view of the pulmonary artery or a parasternal short axis view at the level of the base that gets both aortic and pulmonic valves. Sometimes it is possible, not sometimes, frequently it is possible to identify that lateral border better when you put color, so you can do that. And then again, we get the flow through the right ventricular outflow tract. Notice one closing click, and we combine them in the Doppler equation as we talked in the very beginning to get flow through the RV outflow tract. For mitral inflow, we need the mitral annulus area, and we need to get the time velocity integral through the mitral valve. Here we acquire at the level of the mitral annulus, not at the tips. If you are interested in looking at diastolic parameters, then you place it at the tips. So our usual protocol is to put the pulse wave Doppler sample volume at the level of the annulus, record several cycles, and then go to the tips and record other cycles. One does not substitute for the other. If you use the Doppler signals from the tips to quantify flow, there will be estimation of the actual flow. Let's look at quantifying mitral regurgitation. So during systole, when the ventricle and systolic volume is reached, the stroke volume part of it is going through the aortic valve. That's the aortic flow. That's the blood that will make it to the rest of the circulation, and some goes back to the left atrium. That's the mitral regurg. And so we can say that the stroke volume is given by the sum of both of these flows. If I am interested in mitral regurgitant volume, then I need to get the stroke volume and subtract from that the aortic flow. Let's look at an example. So this is a case from a flail segment of the posterior leaflet. You see from an apical view a large eccentric jet that is hitting close to the septum. So we start by saying what are the set of measurements that we want. We want the mitral annulus diameter. We want the mitral annular time velocity integral. We want the LVOT diameter. And we want the pulse wave Doppler sample volume through the LV outflow tract. And so we get these values. And then we say what is the flow through the mitral valve during diastole. This is the true stroke volume. And we apply that 0.785 multiplied by the diameter squared multiplied by the time velocity integral. We have that number. For the LVOT, we get the diameter squared 0.785 times time velocity integral. And the difference between them is the mitral regurgitant volume. If you want to express it as a fraction, it's 71 divided by that total stroke volume, which is 113, and there is the regurgitant fraction in this case. This is not the only way we quantify mitral regurg. This is an approach that is exclusively based on Doppler data only. We have other methods that you will hear about, and you want to measure it by more than one method to have confidence in your numbers, that no matter what you use, you end up in the same range. Let us look at aortic regurgitation. So here we look at flow through the LV outflow tract, and we look at flow through the RV outflow tract. The flow through the LV outflow tract exceeds the flow through the RV outflow tract by the regurgitant volume of aortic regurgitation. And so you express that as the numerator divided by the total stroke volume, which is here LVOT flow, and you end up with the regurgitant fraction. Again, this is not the only method, but a method that is based exclusively on Doppler. Now let us switch gears and talk about pressure estimation and pressure gradients. For this, we will need to talk briefly about energy and the expressions that can combine pressure and flow. So energy is defined as the capacity to do work. Work, as you may remember from mechanics, is a force multiplied by distance, and we can remove force and put it in its place the product of pressure and area. Now, area multiplied by distance is volume, and so the product of pressure and volume can give you work. So if I have a right heart cath, for example, and I have pressures in the right ventricle, and I can measure volumes, then I can do the RV stroke work. If you're doing pressure volume loops on the left side, you can use that to quantify the work done by the ventricle. So that's one expression to get you energy or work. Another expression we are interested in is a fluid that is moving. And so let us see what we can do here. So instead of force, we are going to put in its place on that fourth line, mass multiplied by acceleration, and we still leave the distance. If you go here and you say acceleration is velocity divided by time, and you say distance is velocity times time, you will see that it becomes mass multiplied by velocity squared. And because we are interested in volume, not really mass, for moving fluids, we can say mass, remove it, and put in its place density times volume. We're talking average velocity, and that's why you see the division by 2. For potential energy, we would say it is mass multiplied by free fall acceleration multiplied by height. It's the same as the fourth line. Again, we remove mass because we're talking about fluids and put in its place density times volume. And so a fluid that is moving has components both kinetic as well as potential. Let's take a look at the expressions that combine these two forms of energy. Before we go there, let's look at a cross-section of a vessel or a long axis view of a vessel showing two different cross sections. At level 1, a larger area, and at level 2, a smaller area. The flow at these 2 points is the same, and the flow is given as the product of area and velocity. And so it follows that where the cross section is smaller, the velocity is higher. In other words, at point 2, the kinetic energy, which is determined by the velocity squared, is higher than at point 1. So let us say, again, these 2 points, 1 and 2, and we want to look at the total energy. It is the 3 components you saw on 2 slides before this one. The product of pressure and volume, the kinetic energy expression, and the potential energy expression. Since we are interested in energy per unit volume to simplify the expressions later on, we divide by volume, and so at point 1 it's pressure at point 1 plus half multiplied by the density velocity 1 squared, and the same for potential energy. Because the vertical distance for points 1 and 2 above the center of gravity is the same, meaning h1 is equal to h2, that expression gets reduced to pressure point 1 plus kinetic energy point 1 equals pressure at point 2 plus kinetic energy at point 2. We are interested in estimating the pressure gradient, so we rearrange that expression and you end up with that. When the velocity at point 1, say, is so much smaller than the velocity at point 2, its square is also much smaller than the square at point 2, and so we can ignore V1. And now the expression becomes the pressure gradient is given by half multiplied by density multiplied by the velocity at point 2 squared. That's the modified Bernoulli, or a prelude to the modified Bernoulli equation. This is the full modified Bernoulli equation that you all use. Basically, we end up expressing the pressure in millimeters mercury and the velocity in meters per second, and we say the pressure gradient equals 4v squared. For someone who says, why is it 4v squared, that slide goes through that explanation. Basically, if we apply the SI units and say we are going to use the velocity in meters per second, and we put the density of the blood at 1.06, and then we convert the velocity from meters to centimeters, so per second, we multiply that by 10 power 4, and then we know the pressure that 1 millimeters mercury exerts. If you divide that numerator by 1333, you end up with a 3.97, or that 4v squared. Is this a perfect expression or an acceptable expression? Most of the time it is, but the full Bernoulli equation is not what I just showed you. It includes a kinetic energy component plus an inertial component plus some energy that is lost due to resistance. At the point where the velocity is maximum, the differential of that velocity is 0, and so we ignore that inertial term. But we cannot ignore the frictional term. If it's a normal circulation, even though we ignore it, the error that we encounter is not that large. But at valve opening and closure, the inertial term cannot be ignored. Further, if you're looking at a peak velocity proximal to where the stenosis is of at least 1.5 meters per second squared, and you ignore it, there will be a problem with the pressure gradient calculated. So if you're presented with a patient who, say, has a peak velocity through the aortic valve of 5 and an LVOT velocity of 2, and you are asked to get the pressure gradient, you have to include the 2 meters per second in the LVOT. That is, use the V2 squared minus V1 squared expression, not just the 4V squared. The pressure gradient calculations have been applied for many situations that we see day to day: pulmonary artery pressures, gradients across stenotic valves, prosthetic valves, dynamic intracavitary gradients, trying to estimate the first derivative of LV pressure and RV pressure based on the mitral tricuspid regurgitation jet, LV end diastolic pressure using the AR jet, and LAP using the mitral regurgitate. Let's go through examples. So the one that we frequently do is the PA systolic pressure. We say that the difference between RV systolic pressure and RA pressure is given by 4V squared. And so what is the velocity here. The velocity we're talking about is the tricuspid regurg peak velocity. I have to get the peak velocity, and we get it from multiple windows. And then we put that expression and say the RV systolic pressure is 4V squared plus the RAP. If there is no pulmonic stenosis, then the RV systolic pressure is the same as the PA systolic pressure. So that's how we go about PA systolic pressure estimation. We can also use the modified Bernoulli equation to estimate the PA diastolic pressure. Here we say the end diastolic velocity of pulmonary regurgitation here is related to the pressure gradient between PA diastolic and RV end diastolic pressure, and again that 4V squared. We make the assumption that the RV end diastolic pressure is very similar to the RAP, and the reason I make that approximation is because I can estimate RAP. It is more challenging to estimate RV end diastolic pressure. So then it becomes 4V squared plus RAP, and that's how we go about PA diastolic. Aortic stenosis jet, we get the 4V squared, and that will get you the peak gradient. Remember, if the proximal velocity is at least 1.5 meters per second, it is no longer 4V2 squared, but we have to say 4V2 squared minus V1 squared. Example of mitral stenosis. You can get the peak gradient and you can get the mean gradient. This is an example from someone with severe mitral stenosis. The peak velocity in early diastole is more than 2, and at end diastole is more than 2, meaning no matter not much blood has left that atrium and the pressure is marked. Estimation of pressure compared to cath is here. This is someone with a mitral Hancock prosthesis, a prosthesis no longer used. It shows the Doppler gradients, and it shows the actual cath gradient based on catheters in the LA and the LV. You see here that by cath it is 10 for the first beat. There is a lot of beat-to-beat variation because of the atrial fibrillation. You can, if you go beat by beat, they are almost identical, 10 for 10, 14, 14, 15, 14, and so on. So if we are well aligned, we get very good and correct estimations of mitral gradients during diastole, be it a mitral native stenotic valve or a prosthetic valve. The dynamic gradients in the left ventricle, say someone with hypertrophic obstructive cardiomyopathy, and we have a dynamic obstruction present. If we get the peak velocity and we do the 4V squared, that will tell us what the gradient is. A small application, this is not done really day to day in the lab, but maybe more for your information, part of the knowledge base that you would want to know, is the estimation of the dp/dt for the left ventricle from the mitral regurgitation jet. Basically, we say we will get the pressure gradient between two time points. One where the velocity is 1 meter per second, and one where the velocity is 3 meters per second. And so if you do the modified Bernoulli, you will say at 3 meters per second, the gradient is 36, and at 1 meter per second, it is 4, and so the numerator here is 32. And then you know the time interval between them, and you measure that from that Doppler recording. In this case, it's 67 milliseconds, and so you divide it by 0.067 to get it in seconds, and you end up with the dp/dt calculation. The assumptions that are happening here is that the only reason the gradient is changing is because the ventricular pressure is rising and nothing is happening in the atrium. If someone has very mild or trace mitral regurg, that's a valid assumption, but say this is a significant degree of mitral regurgitation or someone with a very stiff left atrium, we cannot ignore the atrial pressure in the calculation. You can do the same for the tricuspid regurg, though it is not done, say with calculations. You can look at the shape of the signal. For example, if we look at these two ventricles, this is a situation where if you look at that yellow arrow, the pressure is, or the velocity is rising fast. Whereas in this ventricle with worse function, it is rising slowly, indicating that systolic properties of that right ventricle are not as normal. The last example I'll show you is aortic regurgitation, and someone says, how can I use that for end diastolic pressure estimation? So here we go for the end diastolic velocity, and we say 4V squared is equal to the present difference between diastolic blood pressure and left ventricular and diastolic pressure. I make the assumption that the diastolic blood pressure I get by the cuff is the same as the pressure in the aortic root. And so if that is 70 and the peak velocity is 3.6, you plug the numbers, you end up with an end diastolic pressure of 18. There are problems with this approach, but I introduced it mostly for concepts of how to use the pressure gradients and the modified Bernoulli equation to do some estimates of actual pressures and not just pressure gradients. I'm going to stop here and we can take questions. Okay. So the content that you should be comfortable with includes how to quantify flow, what are the potential sources of error when you quantify flow, be it in the area or in the velocity. Need to know the modified Bernoulli equation, its limitations, situations where it shouldn't be applied, where you should include the V1, and then all of these examples, particularly pulmonary artery pressures estimations, dynamic intracavitary gradients, mitral stenosis gradients, aortic stenosis gradients. Okay? Thank you.